Hi, everybody. Just wanted to take a minute to share answers to the final exam review key in case you had a difficulty in any way with finding the material in your past quizzes or in the slides. So here we go. Also, don't forget, print this out as a paper copy so that you can complete your own key on a separate sheet of paper and use that sheet of paper then while taking the final exam. It's just kind of the easiest way to go about it and the most efficient way for you that will help you as you go. So here we go. Here's the answers to the key to the final exam. Number one, what causes the apparent motion of the stars in our sky? And this is the rotation of the Earth. All right. Number two, when viewing the stars from your local horizon in Geneva, and this is a select all that apply here, the point directly above your head is called the zenith point. Yep, that's definitely a thing. You would be able to face 45 degrees azimuth. Yes. You can see stars rising in the west. Nope, stars rise in the east and set in the west. So that's not one. And then you'd be able to see the Big Dipper. And you certainly can in our sky. Okay. Number three, your angle north or south of the equator is listed on parallel lines on a globe and is called. So your angle north or south of the equator is latitude. All right. For some reason, people struggle with that one, so I'm glad we were able to talk through it here. Stars in Australia rise in the east and set in the west, just like anywhere else on Earth. They're not all circumpolar. They're only all circumpolar on the north or the south pole. Rise in the east and set in the west. Mm-hmm. And appear to spin around Polaris? No, because you can't see Polaris in the Australian sky. Number five, the ecliptic. Check all that apply. The ecliptic is the apparent path of the sun in the celestial sphere. Yes, that's definitely what the ecliptic is. Um, it is about where the planets appear along the celestial sphere. That's also true. The apparent path of the Earth around the sun. Yeah. Mm-hmm. And it's tilted 23.5 degrees off the celestial equator. That is also true. And that is because of the actual tilt of the Earth. It makes the sun's path in our sky tilted. So all of those apply here. There are blank time zones, one for every 15 degrees of longitude. That's 24. There are 24 time zones around the Earth. We are in the central time zone. There are 23 others. Know the full position of the new first and third quarter moons, as well as the position of the solar and lunar eclipses and the spring and neap tides. All right, so let's go ahead and put a text box on this so we can label. We'll just go ahead and label it full moon here. Let's make sure we don't have any outline. And let's color this real quick here. All right. Okay. So this is where the moon is when it's full. Happened. Uh-oh. Why is that doing that? Well, this, hopefully we can get this to work out here. Whoops. Let's copy and paste this one here. All right. So this one is we're in its first quarter. And it's The moon is in first quarter here. It's in third quarter on the other side at position 7. Move that up here. And we know that the moon and the sun pull on the earth in the same direction during spring tides. So spring tide occurs twice a month when the moon is new and full. So this would be spring tide over here and spring tide over here. And it's a neap tide when they pull against one another. So neap tide would be position 7 here and position 3. Okay. Also, we know that a lunar eclipse happens when the moon is on this side of the sun, and a solar eclipse happens when solar is eclipsed from our view. The moon is blocking it, so it's got to be on this side of the sun. So solar eclipse would be position 1 over there. Okay, so there we go. That's a look at the diagram. That should help you out greatly when it comes to taking the quiz on this. Why don't we see an eclipse every month? And this is because the moon's orbit is tilted 5 degrees off of the ecliptic. And precession is the Earth's wobble. The declination of the sun at the summer solstice is plus 23.5 degrees. It's minus 23.5 degrees at the winter solstice. The Earth has seasons not because of its varying distance from the sun, because it is tilted, spherical, and revolves. The directness of changes directness of sunlight changes over the course of the year. These two are why the Earth has seasons. This causes this, and they're both related to seasons. It's not how far or how close we are from the sun. Of the months of the years listed, when is the Earth closest to the sun? And that is in December. January is not listed. That's when it would be the closest. End of December, beginning of January. What are the seasons like on Uranus? And they are extreme. And this is because of the extreme tilt, the 98-degree tilt of Uranus. Check the box with the correct civilization for each of the items below. So I guess I could just label each of these. Observations of a supernova explosion. This is the Chinese. And used stars for navigation. This was the Polynesians. And created the zodiac. This was the Babylonians. Use stars to determine when to plant crops. This is the Egyptians. All right. Aristotle was the one who was basically the father of the geocentric theory. He was the Earth-centered Greek guy. Aristarchus was the sun-centered Greek guy. So he was determining by the phases and eclipses and the geometry of that, he was able to determine that the universe was heliocentric. But Aristotle was much more influential. Copernicus, he was the Renaissance heliocentric guy. Kepler was the planetary laws guy. He was the early 1600s. His first law was about orbital shape, that orbits, planets and satellites orbiting ellipses. The second law was about speeding up at perihelion and slowing down at aphelion. It was also known as the law of equal areas. And the third law was that the period squared equals the distance cubed. And this was how he related those. Newton came along in the mid-1600s and described lots of things in his 3 laws of motion. The first law was about inertia. and all motion describing velocity, acceleration, things like that. His second law was also known as the law of force, and it had the equation force equals mass times acceleration. Newton's third law was for every action, there's an equal and opposite reaction, basically forces interacting with one another. And so that was Newton's laws. Tycho Brahe was the person that actually got all that precise and accurate measurements so that Kepler could do his planetary laws. So he was the precise and accurate measurements person in the late 1500s. Galileo was the one that used the telescope to study the sky in the early 1600s. He also, using the telescope, he was a heliocentrist, so he's not a geocentrist, but he also discovered the moons around Jupiter, sunspots. He discovered that the moon had valleys and vast plains. He also discovered that Venus had phases. Newton, of course, did describe gravity. He was a heliocentrist. He did invent calculus and came up with the three laws of motion. So he did all of these things. Gravity, which we talked about Newton describing here, was an acceleration of due to a force acting on something, and it's what causes planets to orbit the sun, among other things. Inertia was as part of his first law, so that's not one of the answers here. One astronomical unit is about 150 million kilometers. That's true. It's also the average distance from the Earth to the sun. And it is longer than distance from the sun to Mercury. So that is the three there. Temperature, for number 29, is a measure of kinetic motion. It is lower in slower moving molecules. It does relate to atmospheric thickness, so that one's not a thing, and is related to escape velocity of gas molecules. If they're moving faster, they're going to escape the planet a lot easier. So temperature are these three things. And it is related to the atmospheric. The thicker the atmosphere, the colder the temperature. A planet's atmosphere does distribute heat and act as a blanket for the planet. It will be thick if the gravity is large, so this one doesn't apply down here, and can produce adequate pressure to allow liquids. That is true as well. So it's these three for the planet's atmosphere. The Jovian or terrestrial for each, given the characteristics. Thin atmospheres is terrestrial, as is a metallic core. Terrestrial planets also have the overall density between 3 and 5. The Jovian planet's density is much less, and they are associated with the gas and the ice giants. Okay, so that is the answer for those. Earth is a terrestrial planet. Jupiter is a Jovian planet, of course. It is a gas giant. We would consider Neptune and Uranus ice giants. Oh dear, got to be consistent here. Okay, what is the main gas that makes up the atmospheres of Venus and Mars? And that would actually be carbon dioxide. Venus and Mars are primarily carbon dioxide, whereas Earth is primarily nitrogen. A planet's magnetic field forms a shield protecting the planet's surface. The charged particles that are coming from the sun that hit the Earth are called solar wind. Two things that are required to produce a magnetic field are a liquid metallic interior and rapid rotation. This is what's going to produce your interior magnetic field. The type of planet represented in the diagram. I didn't have my diagram in here. The diagrams I'm referring to are the terrestrial versus Jovian diagrams. Let me see if I can call one up here. So I'm not going to get, you obviously won't get the exact answer here, but you'll be able to surmise it. From the diagrams. Now, actually, if I go to astronomy, I think astronomy notes would probably be better here. Of course, you can get a lot of these answers from your notes. Obviously, all the answers from the notes. You can also get these from the, let's see here. You can also get these from astronomynotes.com, which is where I'm getting these here. So let's take a look at, I think we're going to find terrestrial versus Jovian here. Don't quote me on this. Okay, maybe not. Let's see here. Maybe in our planetary interior section. There we are. That's the diagram we're looking for. We'll bring this over here. Terrestrial versus Jovian diagram here. You'll see on the quiz here. Okay. And so you're just going to need to study that one. All right. Why is Venus so hot? And that is runaway greenhouse effect, where the rocks, the carbon dioxide in the rocks get baked out from the heat. And then after they get baked out, the temperature gets higher because there's more carbon dioxide in the atmosphere. And then which bakes out more carbon dioxide, et cetera. It's a feedback process. Okay, what causes large dust storms on Mars? And this is the difference in temperature between day and night, which is a very, very large difference. And so oftentimes the circulation that ensues from that is very large. Dark, smooth areas on the surface of the moon are called maria. These are vast lava flows of basalt lava. They were thought to be seas, and so the word maria means sea in Latin. The largest moon in the solar system is called Ganymede. It circles Jupiter. Titan is the second largest, and it circles Saturn. The greatest chance for life outside the Earth exists on Europa. It's thought to have a deep saltwater ocean underneath it. Perhaps the interface of the surface of the bottom of that ocean with the water could create like a underwater volcano situation, providing the energy necessary for life as we know it. What is the most widely accepted theory on how the moon was formed? That is that the moon or the Mars-sized object came and smacked into the Earth. That material ejected from the Earth into orbit and then eventually formed up into the moon. This is the collision of the two. All right. Spectroscopy is using prisms in order to split up the light into different wavelengths and then study those wavelengths of light. So spectroscopy is a use of several telescopes. Nope, that's using an array. Uses a prism to separate light into different wavelengths. Yep. Is the scrunching or stretching of light waves due to motion? Nope, that's the Doppler effect. Is the study of light spread out into its different colors? Mm-hmm. Involves redshift and blue shift? Nope, that's the Doppler effect. The Doppler effect is the red shift and blue shift, and that happens because the light waves are stretched or scrunched due to the motion of the object. All right, light, what do we got here? Check all that apply. Is referred to as electromagnetic radiation? Yep. Is created by nuclear fusion in the core of a sun? Yep. Doesn't have all the characteristics of a wave? Yeah, it does have the characteristics of a wave and comes in many different frequencies, wavelengths, definitely. All right. Review what a radio telescope and a reflecting telescope look like. You'll be given a diagram of each to identify. When looking at this, I suppose we can do, we have diagrams in the notes that you can look at on these, but of course there are diagrams online here as well for you to see, and the differences between the two. So let's see here. This one's a bit more labeled than the other. So we'll go ahead and copy and paste this image in there. but this will help us review those. Here. There we go. The total amount of energy radiated by a star every second over its entire surface area is called luminosity. And you measure luminosity with flux, which is just the amount of energy out of a square of the star. Hot stars have a tendency to appear more blue in color than the others. So blue hot is hotter than red hot. In the graph below, which is the HR diagram, this is showing temperature and how temperature relates to color and spectral class on the x-axis, x-axes, and the y-axes have the absolute magnitude and luminosity here. So, which is the brightness and the energy output, and those are directly related. So there's a direct relationship between luminosity and absolute magnitude. White dwarfs are among the brightest. White dwarfs are down here, and bright is up here. So no, white dwarfs are the dimmest. This is called the HR diagram. Our sun is a G2 star. It have a temperature around just under 6,000 K, and that is true. G2 stars would be right about here, and so when you're looking at them, you come up at 1 solar luminosity, our star would be right about here. Shows that red giant stars are on the cooler side of most stars, and that's definitely true as well. Red giants are over here, and you can see that the temperatures are cooler on this side, on the right side of this diagram. All right, according to the graph below, the peak wavelength of Sirius is right here. And so when you come down here and take a look, that is right at about just under 4,000 angstroms, so about 3,900 angstroms. And that would actually be peaking in the blue part of the spectrum here. So it's Sirius is a blue hot star. Put a check mark next to the two most abundant gases in the sun, hydrogen and helium. Okay. And then the parts of the sun here, labeling each, nuclear fusion takes place in the solar core. Cooler regions of the surface of the sun are called sunspots. Outermost atmospheric layer of the sun is the corona. Crown. Name for the surface of the sun is the photosphere. And the low density pink layer in the solar atmosphere that's just above the surface, that's called the chromosphere. So the solar core, that's where nuclear fusion takes place. It's because it's so darn hot in there. As you get through the layers of the sun, you get the radiative zone and the convection zone. The convection zone takes the heat up to the surface, which is called the photosphere. And of course, sunspots dwell on the surface of the sun. They are dark spots that are a little bit cooler, where the gases are sinking and or interacting with the magnetic field of the sun. And then the solar atmosphere, of course, that corona is what we see deep into space, but there is a pink layer just above the surface of the sun called the chromosphere. So that is all about our sun. And then we had a matching section on stars and the life of a star. The giant molecular cloud, the gas clump that is basically kind of the material where the star forms up in. The protostar, that is the gas clump that forms from collapsing material due to gravity. So let's see here. And it's hot ball gas. It's not yet producing nuclear fusion. Next, we have explosive stage of the star's development that marks the beginning of the nuclear fusion, which causes the star to be born as strong stellar wind. This is called the T-Tauri phase. Noted that it was a star in the constellation of Taurus that we first see this happening. A super dense ball of neutrons left over after a supernova explosion. This is a neutron star. Term referring to interstellar clouds of gas, dust, and ice that contract under the influence of gravity. So for this one, this is our stellar nursery where stars are formed. This is your um, giant molecular cloud. Smaller star ends its life by ceasing nuclear fusion, releasing a cloud of gas into the area of space surrounding it, filling many kinds of elements. This is called a beautiful planetary nebula, and they are beautiful. A star spends about 90% of its life cycle on the main sequence, which is its middle life. This is where it's balancing its inward pull of gravity, catastrophic inward pull of gravity, is balanced by its catastrophic explosiveness from the nuclear fusion taking place inside the star. It's nice balance. That's called hydrostatic equilibrium. A super hot, relatively small sized ball of white hot degenerate gas left over from a star's death. That's a white dwarf. And these stars are very dim, but they're very hot. Blank is a large explosion caused by the fact that a star reaches iron in its core and the iron will not fuse. And so there's a catastrophic collapse of gravity, which it rebounds outward into a supernova explosion after it kind of crunches down and then rebounds outward. What's left behind then is a black hole or a neutron star. And lastly, toward the end of the life of a star, hydrogen hydrogen gets all used up and fuses into helium in the core, and there's a momentary pause in fusion, and then the star starts to crunch down. That causes the shell of the star to start fusing helium, and so this makes the layers expand way out into space. This is your red giant supergiant phase of the star. And it looks like we don't have a number 65 for some reason. So that is a look at the key for the final exam review sheet. So hopefully that was helpful for you. I'm sure it was. And if you have any questions, again, don't ever hesitate to email. I'd be glad to help. So thank you very much.